Another way you can use the precise definition of a limit is to prove the limit laws that we have been using. So up to this point, you've kind of taken my word for these limit laws, but the way to prove that these limit laws are true is to use the definition of the limit. So let's do that. So as an example, we'll look at the sum rule for limits, and also this composition law down here, which is sort of maybe one of the least intuitive facts about limits. But let's start with the sum law because it's a little more straightforward. So let's prove that if the limit of f as x approaches a exists and is finite, and the limit of g of x at a exists and is finite, then the limit of the sum is the sum of the limits. So remember, to show that a limit is what you think it is, you have to, for every epsilon, you have to find a delta. So let's suppose that we have some positive epsilon value. Now we need to find a delta that works. And remember, delta is usually a function of epsilon, and exactly what function of epsilon you choose here really depends on what it is that you're trying to show. And it can take some trial and error, but I've sort of done the trial and error ahead of time, so I know that what I want to choose for delta depends on these individual limits here. So before we can choose delta, what we need to do is since we know these individual limits exist, we can actually use this property. We know that this property is true for f and g separately. So by the definition of the limit, there is some delta. We're going to have two deltas floating around, one for f and one for g. So I'm going to call this one delta 1. There is some positive delta 1 so that if the distance between x and a is less than delta 1, then the distance between f of x and, here I'd better name this limit, let me call it L, and let me call this one M, then the distance between f of x and L is less than, so I can choose anything here, and I'm going to choose, instead of epsilon, I'm going to choose epsilon over 2. Okay. Now also, by the definition of the limit, right, so what happened here with f is that instead of choosing epsilon, I chose epsilon over 2 to use this definition. So the definition then says, for this epsilon over 2, there is a delta that works. Right, so that's what we have here. Now for g, by the definition of the limit, there is a delta, which we'll call delta 2, greater than 0, so that if absolute value of x minus a is less than delta 2, then absolute value of g of x minus m is less than epsilon over 2. Okay, this kind of sets the stage. Now what I need to do is pick my overall delta. Right, so I'm going to let delta be the minimum of delta 1 and delta 2. In other words, the smaller of the two, right? So, and let's suppose that we have an x value so that x minus, the absolute value of x minus a is less than delta, right? So by choosing the minimum, since this x value is delta close to a, it's actually also, it's delta 1 close to a and delta 2 close to a. So by choosing the minimum, getting x this close to a gets me close enough for this and close enough for that. So that's why I have to choose the minimum here. Okay, so now let's calculate the distance between f of x plus g of x minus the sum of these limits, right? This is what we're hoping is less than epsilon. If we can show that this is less than epsilon, then we're done. So we can rearrange the stuff inside the absolute values here. So this is the absolute value of f of x minus L plus g of x minus m. Okay. But the way absolute values work is if you have a sum inside of an absolute value, that's less than or equal to the absolute value of each separate piece, right? So this is absolute value of f of x minus L plus the absolute value of g of x minus m. Okay, but because we know that we're close enough to A, we can use these properties. So this first absolute value, we know that has to be less than epsilon over 2. And we know this second absolute value has to be less than epsilon over 2. But these add up to epsilon. Now you see why I chose epsilon over 2. So we had an epsilon, we found a delta, and that delta works. And that means that this limit is this value, which is what we said it should be. So that proves the sum law for limits. Let's see how we can use the definition of a limit to prove this composition property. So the composition property of limits is that if you have a function g whose limit at a is L, and you have a function f whose limit at L is m, then the limit of the composition at A is m. So this seems plausible, but you have to prove it. It's not really clear, without the precise definition, it's not really clear why this is true, I think. So let's suppose we have some epsilon that's positive. Now we need to. Now epsilon is sort of on the output side, so we should, since f is on the outside, we should start thinking about f. So by the definition of the limit, and I'm really thinking of this limit here, there is a delta that's greater than 0, so that if the distance between x and L is less than delta, then the distance between f of x and m is less than epsilon. Okay, this is just by the definition of the limit for f. Okay, now delta is sort of getting us close to L, but because the limit of g is L, getting close to L is like getting close to the limiting value for g. So what we can do is use this delta as it's sort of playing the role of epsilon for this limit. So now that we have delta, we can say that by the definition of the limit for g, there is a different delta, let's call it delta 2, positive, so that if x minus a is less than delta 2, then the absolute value of g of x minus L is less than delta. Okay? All right, so now we have the stage set up. We've produced this delta value. So let's, we've sort of set the stage. So now what we need to do is, given this epsilon, we need to choose an overall delta, but it's really just going to be this delta 2. So let's suppose that x minus a is less than delta 2. Okay, we want to know, what does this tell us about f of g of x minus m? Right, we're hoping that this is less than epsilon, so let's see if it is. Oh, sorry, I wanted delta 2 right here. Okay. Well, since x minus a is less than delta 2, this implies that the absolute value of g of x minus L is less than delta. Okay, and this implies that the absolute value of, right here we have this input, for f that's close to L, but that means that the output for f is close to m. And when we say close to m, right, well, this is how close it is. So this is epsilon close. But that's what we wanted to show, so we're done. It turns out that this composition, once you have the stage set, this composition property sort of proves itself almost. So, right, the sort of general thought process here is, if we get really close to A, right, this is saying if we get really close to A, then we get reasonably close to L, and if we're reasonably close to L, then we're epsilon close to M. And that's what we wanted to show. So this proves that when you have if you have these limits set up in this way, the limit of a composition is what you think it should be.